Hey guys, let's continue with part 2 of our bonding review. Again, a lot of this stuff is stuff that you probably know from Chem 1 or maybe even from physics or something like that. I just want to review this stuff. This stuff is obviously bonding is pretty vitally important to what's going on in any chemistry class, but particularly in organic. And we're going to start to talk about some of the things that make organic a little bit different here as well. So first off, if we talk about covalent bonding as opposed to ionic bonding, remember that ionic bonding was essentially anything that had a metal in it. So that would be all of this stuff over here on this side of the periodic table. And so if we're going to focus on covalent, it doesn't really seem like there's a whole lot left. Like if we get rid of all of those metals and then we just leave us with, what's left here, okay, then what we're going to see is essentially this little bit of elements. Now, what you'll notice here is that I obviously took out the noble gases here. Okay, they're gone. And then all the metals are obviously gone. This is our staircase here. And so we've got sort of metalloids here. And really, if we eliminate the metalloids as well, so like, right through here, then we're really left with this really sort of small number of elements that are, classically speaking, just the non-metals that are going to form most covalent bonding. And it seems like if you're thinking about the 118 or so elements in the periodic table, and we're trimming that down to, say, 10 or so for covalent bonding, it seems like our diversity is getting a lot smaller, but there are millions upon millions of molecules that are covalently bonded together. And a large part of that is going to be organic molecules in particular, and biomolecules as well. And so this is a vitally important part. Even though it seems like it's taking up a really small portion of the periodic table, it still matters pretty immensely to us. The other stuff matters as well. If you take inorganic chemistry in college, we'll talk a lot more about the metals and those sorts of things. But obviously, we're going to focus a lot more on the covalent bonding. Doesn't mean that you don't have to know about ionic bonding. You definitely do, and there are definitely some ionic cases here. But covalent is what we're going to focus on probably for the majority of the class. So what's the difference in covalent and ionic bonding? If you remember in ionic bonding, what was going on is that we had a transfer of electrons. And so we had something like, say, this, where, you've got a sodium and you've got a chlorine, okay? And we decided that we were going to transfer, that's not going to work. We decided that we were going to transfer one of the electrons, right? So our electron went over here, and that gave the sodium a positive, and then gave the chlorine a negative. So what then is different in covalent bonding from that situation? Well, in covalent bonding, there's essentially no transfer of electrons. The electrons don't move from one atom to another. What happens instead is that they get shared between each other. And so what we've got in the initial situation here is we've got, say, two hydrogen atoms, okay? And they each have one electron, and these two things are going to covalently bond. Now, how do we know that they covalently bond? Because they're non-metals, even though hydrogen's on the left-hand side. Remember, hydrogen's an exception. It can act metallic, but doesn't really concern us. That's more of an inorganic thing. But it's a non-metal, and so we're going to get covalent bonding. And essentially what's going to happen is that they're going to overlap, and what they're going to do is they're going to form a bond between them. So this shared pair here forms what we call a covalent bond. So this right here, okay, is what we call a single covalent bond. A single covalent bond basically just means that there is a pair of electrons that is being shared between two different atomic nuclei. It doesn't just have to be a pair. It could be more than one pair. That's multiple bonding. We'll get to in a little bit. But it has to be at least one pair of electrons. It takes two electrons to make a complete bond. And you know what, you guys, I don't mean to be like one of these old fuddy-duddies that says like, oh man, you guys don't know how lucky you are, but like you really are in terms of science, because it's only now that we're actually able to see this. These pictures came out this year in 2013, and they're just so amazing. This is actually an organic molecule here. You'll see that this is the original molecule. And what you can actually see is that, if you look really closely, you can see the rings here. We'll find out later this year those are aromatic rings. You can see the concentration of electrons in certain areas, and then you can actually see new bonds forming to form these new molecules. And that's just amazing. I mean, we weren't able to actually see these things until the past 10, 20 years. I mean, we could sort of do X-ray crystallography and see a little bit about, what maybe the atoms are like. But to actually be able to get to this level where we're seeing the bonds, I mean, There's just immense stuff, really cool stuff out there for those of you all that are going to go into some sort of science field, particularly if you're going into chemistry or physics or biochem or something like that. Really awesome stuff that you guys can do. Now, I highly recommend that you go look this up. I got it from a Wired article here you can see at the bottom, but go look this up and read a little bit about it. It's really amazing the stuff that they can do now, that we can actually see atoms, that we can actually see molecules and see bonds forming in a way that we never could before. And so that's pretty cool. So back to the covalent bonding. Sorry, guys, got a little excited there. So this is a single covalent bond. There's sharing of electrons there that happens. So let's go over some terminology here that matters for us when we talk about these covalent bonds. The first of these things is something called bond length. Not all bonds are equal. Basically, every atom-to-atom bond, where you got two atoms, okay, is different. It's different not just between what atoms are bonding together, but it also matters what, say, this atom over here is actually bonded to. If it's bonded to other stuff on this side, it's going to influence this bond a little bit as well. So there's all kinds of things that go into it. So basically, we've got these averages here of how long the bond lengths are. So if we went back to look at this picture, you'll notice they're talking about little a with a circle over it. Those are called angstroms. And so, they're showing how tiny these things are. An angstrom is 1 times 10 to the 8th centimeters. Okay, so 1 times 10 to the negative 10th meters. So basically a 10 billionth of a meter is an angstrom. So we're talking, obviously almost beyond microscopic, just now getting in the range where we can actually see these things. But what you'll see here is that each bond between two different atoms has a characteristic length. And you can look these up. If we pulled out a CRC Handbook of Chemistry and Physics, we could actually look up these values. You'll have charts of them that we'll see. And of course, you can always just Google it and say, hey, I need a bond length chart, and pull that guy up, and it would say, okay, these are your bond lengths for these certain bonds. And you'll see that each one of them is different, right? So a hydrogen to hydrogen bond that we just showed in the last slide there, pretty short bond, and then a hydrogen-fluorine bond is a little longer. Some of that obviously has to do with how big the atom is. I mean, fluorine atoms are bigger than hydrogen atoms. I mean, if we drew them, okay, so if we drew if we drew a hydrogen atom, we'd have an H in the middle, and then we'd have one shell. And then if we drew a fluorine, sorry for my awesome artistic skills, we would have two shells. And so obviously it's going to be a little bit bigger. The distance is going to have to be a little bit longer because these atoms can't get quite as close together as they could if they were both H's. And obviously as you get a little bit bigger, that's going to tend to increase, and your bond length is going to be a little bit longer. So you can see here a carbon-to-carbon bond, obviously going to be a little bit longer because the carbons are both a little bit bigger than the fluorine atom, and so that's obviously going to much bigger than hydrogen, so they're going to be spread out a little bit further. So bond length, what's the distance between the nuclei, essentially, of those atoms? Bond energy. This is super important to us. We're going to talk a lot about this throughout the course of the year. If you take AP chemistry or physical chemistry, and where you're talking a lot about the energy and thermodynamics behind things, then bond energy becomes super important. And essentially what it is how much energy is stored in one of those bonds. What do I have to put in to get one of those bonds to break? I mean, a lot of what we do, if you're burning gasoline in your car, what you're doing is you're breaking down the bonds between all those molecules in the gasoline, a lot of octane molecules and some other stuff. And so you've got to put some energy in initially to break them, and then as they break apart, as you combust them, that's going to give off energy as well. And so the bond energy there becomes really important to us. That obviously, as you can see here, changes between different kinds of bonds. So hydrogen bonds, relatively energetic, but we start to get a little bit higher here. You see the carbon-carbon bond obviously takes less energy to break that than it does a hydrogen-to-hydrogen bond. Okay, that has some pretty important consequences as well. One of the ways that we separate out, say, petroleum when we get it out of the ground is we have to separate it into, natural gas and gasoline and asphalt and all those things. And one of the ways they do that is through a process called cracking. And that process largely works because you can break these carbon-carbon bonds a lot quicker than you can break the hydrogen-hydrogen bonds. So that will let you break the molecule up from its long chain of carbon molecules. So there are two really big things that are going to affect this. One of those things is the electronegativity difference between the two atoms. And the other one is obviously going to be the bond length. It tends to work that the longer the bond, then if the bond is longer, then typically speaking, the bond is weaker. And that kind of makes sense. I mean, if you've got a long board and you want to break it, it's a lot easier to break that than if you had a little board. If you were in karate class and you were trying to hi-ya on top of a board, if it was if it was 6 feet long, you wouldn't have to put nearly as much energy into it because it's not going to be as strong in the middle. If you've got a board that's 6 inches long and you try to chop that, you're probably going to break your hand. And so that same general principle is going to be true there as well. And remember, we talked last video about the electronegativity. So if there's a big electronegativity difference, then that's going to change the bond character as well. So in this HF bond, even though the bond is longer than the HH bond, there's a lot more electronegativity difference, and that's going to hold them together a lot tighter than the HH bond. And then you see here double bonds, and we'll talk more about those in a second. Double bonds are going to be much stronger than single bonds. All right, so polar covalent bonds, this is something that's super important. We've only talked so far about really, we've shown some, but mostly non-polar bonds. We haven't mentioned, we just said there are covalent bonds. Really, there are two types of covalent bonds. There are non-polar bonds, and non-polar bonds are those like this HH molecule here, where you've got two things that are either the exact same atom bonded together, or they're two atoms that have pretty similar electronegativities. So like if we had a C and an H bonded together, their electronegativities are not very different. 2.1, 2.5, not that different. And so they're going to be relatively non-polar. But if you've got a big difference in their electronegativities, okay, as we do in the case of chlorine and hydrogen, chlorine's got a 3, hydrogen has a 2.1, that's going to be what we call a polar covalent bond. And all that means is that the electrons, even though we're sharing the electrons, that we're not sharing them equally. So like me and you could share a piece of pizza, or I'm share a piece of pizza. Hopefully we share a whole pizza. And so let's say that pizza had 8 pieces, but let's say that so I say, hey, we're going to sit down, we're going to share these. If I eat 6 of them and you eat 2, we've shared the pizza still, but we didn't share it equally. I got a bigger share. And that's exactly what's going to happen here in polar covalent bonds. So if we look at this polar covalent bond here, what happens is the chlorine gets a bigger share of the electrons than the hydrogen does because it has a higher electronegativity. So basically, the bond here, the electron cloud sort of shifts and it's a little bigger on this side. What that does is it gives this end of the molecule a slight negative charge. The little delta here, this is a delta sign, a lowercase delta, and that means a slight negative charge and a slight positive charge are what we get. And that has all kinds of profound implications. Back when we talked about intermolecular forces in Chem 1, this is one of the biggest ways that we have intermolecular forces. If we got polar bonds, then the molecules themselves want to hold on to each other. This is what makes water such a weird, freaky molecule, is because it has some really strong polar covalent bonds in it. And we can also indicate this by this symbol. Instead of just drawing these deltas here, we could also sort of say, hey, this is the direction of the polarity. This is sort of a dipole moment here is what we would say this is. Positive charge down here, and then the end of the arrowhead would be the negative sign. It doesn't have to be between hydrogen, obviously. We're talking about organic chem, so carbon matters to us. So we could have it between carbon and some other molecules. Now, what you'll notice here is that carbon to chlorine, again, not that massive a difference, so it's not going to be a terribly polar bond. A little bit more so than maybe a carbon-hydrogen, but not a whole lot. But what if we had, say, a carbon to oxygen bond? Well, in that case, we're starting to get a lot more polarity there. We've got a whole 1 point of electronegativity difference. Going to have a negative over here, and a positive over here, and that's going to profoundly affect how those molecules interact with each other. We'll talk more about that later in the year. Sorry, the video's getting a little long. I got to speed it up a little. So carbon, obviously organic chem, we're talking about carbon, right? Carbon is pretty special. So we're talking about covalent bonding. Carbon does covalent bonding pretty cool. It's got 4 valence electrons. You'll notice that they're all sort of single covalent or single electrons. There's no pairs there. And what that essentially does is if you couple the fact that there are 4 valence electrons with the fact that it's kind of in the middle of electronegativity values, that means that carbon doesn't like to form ions at all. Carbon pretty much, not always, but pretty much forms covalent bonds, and it pretty much always forms 4 covalent bonds. That is super valuable. That means when you start to draw these structures and you're trying to figure it out, keep in mind we're looking for 4 covalent bonds when we draw that out. So what does that look like? Well, all kinds of examples. If we just have 1 carbon, then we've got things like methane, okay, natural gas, chloroform, carbon tetrachloride. You'll note that in each of these, carbon has 4 bonds. And anytime this year you're drawing structures, carbon should have 4 bonds. If you've drawn a structure and carbon doesn't have 4 bonds, You need to go back and check it because there's probably something wrong with it. And what also makes carbon really cool is that since it can form 4 bonds, it also has this ability called catenation. And what catenation is it basically means that the element can form these really long chains of itself by covalently bonding together. Sort of like, they're not technically polymers, but that's almost what they're like, is that one atom is going to form a whole long chain of itself in various branching ways. And that's, of course, the beauty of organic chem, what we're going to be talking about all year. Carbon's not the only molecule that does this, but it's the best. Silicon can do it a little bit. Sulfur can do it a little bit. Phosphorus does it a little tiny bit. Selenium does it, but carbon is the best. And of course, that's what makes carbon so unique to life and living organisms as well, as carbon does this catenation so well. And since it can chain itself together in these long chains, there are all kinds of different molecules then that we can make out of carbon. And so that's what makes it so important. One last thing before we jump out of here. I sort of briefly talked about this before, but we can also have multiple bonds. Okay, we don't just have to have single bonded things together. We can double bond things together. So we could say bring these 2 oxygens together here. Okay, so that they're essentially sharing 4 electrons between them, and that actually is how oxygen exists in nature. Generally speaking, it's O2. We could have triple bonds. Nitrogen in the atmosphere is N2. It's triple bonded together. And of course, why does that matter for us? Because we're worried about carbon, right? And so carbon, of course, can form double bonds. It can form triple bonds. I want you to notice real quickly here that each of these carbons has 4 bonds. And if I hadn't put 4 bonds on each of those carbons, I would know that my structure here for this ethene would be incomplete. And so I would have to add some extra stuff into it. But now I know that it is complete. And I'm going to wrap up there, guys. We're going to talk a lot more about how unique carbon is and some isomerism and all that stuff in the next video. But hopefully that gives you some ground to stand on and a little bit of review of previous material. Thanks, guys.